You're all going to fail that one.
Switch to Windows.
That's fair. Actually, it shouldn't make a difference because Eclipse is written in Java. So I don't think there's an actual physical difference between Eclipse for Windows and Eclipse for Mac.
You don't think there's a physical difference?
Other than Java runtime.
Really?
I don't believe so because the application is written in Java. Or at least I'm gonna let's say 92% certain.
That's lower than usual.
Yeah, it is, but it's still a high percentage.
Let's do that question. How to fix
Yeah, but then everybody would fail it because nobody told me how to fix it.
delete it and then reinstall the thing.
Well, yeah, that's usually what I say to do.
Go.
Well, I'm not going to do that because I'm too lazy and I'm too stubborn. We already covered that with the ointment situation.
Turn it off and on.
Did you turn it off and on again? Let's see, what class is it? 325. Here we go. Okay, shut up! Oh, by the way, speaking of which, I hear that there's an inside joke where you guys yell that in the dorms. Is it mocking or mimicking?
Mimic. It's flattering. We like it.
Yeah.
I actually don't care whether it's flattering or not. It's all right. None of your other teachers tell you to shut up? Really?
They just cut you. You don't shut up.
Oh, they attack. What teacher does that? It's got to be some theology prof.
Fire brimstone.
That's probably would be the scariest thing if you had a theology prof that was also a ninja. Isn't there a movie about that? Like, some. Not that.
With that premise.
I think so.
Professor by day, ninja by night.
No, something like it was like some high up cardinal or something like that in the Catholic Church, and the guy was like, I don't know, he was like all into, was it Krav Maga? Yeah, the Israeli, death art or something, the crazy fighting. Yeah, I mean, the guy was just snapping people's necks like nothing. And then like going and doing mass. He was in the back.
Come for this. There have been so many good lines in that.
All right. So a homework assignment for today. We are continuing to work with procedures. So we had a procedure for printing stuff to the screen, right? And then we started working with strings. And so your homework was to, in the data section, define 2 or 3 strings. I probably told you what to make them equal to, but whatever. 2 or 3 or 4 string variables, and then prove that you have a general purpose display to screen procedure by calling your display to screen procedure for each of your 4 variables, right? Loading them either depending on how you ended up doing it. Did you push it onto the stack, or did you throw it into a register? Whatever you needed to do to, quote, pass the parameters to your procedure and then see it display. That was what we were practicing, right? That was the assignment. Sound accurate? Now remind me, what's the advantage and disadvantage of passing your parameters through the stack to a procedure? What do you have to be careful about when you you push your parameters to the stack as you call a procedure with the call 8086 command?
The first thing that you pop off is going to be where it will return once the procedure is finished.
Okay, so we need to be aware that as a side effect to the call 8086 instruction, a value gets pushed onto the stack, and that is the offset from the base, the code segment, CS register, where the next line inside of your, we could say the main procedure, but where the next line inside of the previous procedure, the procedure that you were in that called this procedure, where it needs to return. So if you want to be able to extract your parameters, you need to pull that guy off the stack and preserve it. Then you can grab your parameters and then make sure before you're done, you get that guy back on the top of the stack so that when you return from your procedure, it can grab the value from the top of the stack and go back. What's a downside to throwing things onto the stack? Besides that. That's a little bit inconvenient, but that's not necessarily a downside, right? That's more of just kind of knowing how the tool works.
I would still list it as a downside.
Okay, give me another downside then of the stack. Passing your parameters via the stack.
It's not as fast.
Not as fast as what?
Just saying, use this register.
Okay, I guess that's probably always a safe answer when you do. Like, nothing's as fast as registers. So you're right, it's not as fast. Okay, so other than that, what else?
You have to keep track of where it is in memory.
Okay, tell me more about that.
It's harder than just dealing with one register. You have to pop it in all the stack. And I guess that's part of managing what the call procedure puts on the stack.
Let's say you have two parameters you're passing to a procedure,
Yeah.
and you push those guys onto the top of the stack. Which parameter is which? They're anonymous, right? You have to remember. So if you wrote a procedure a month ago, you have to remember that the first value you pop off the stack, well, second value after you pop off the offset from the code segment, that you pop off is parameter 1, and then the second guy we pop off is parameter 2, as opposed to the other way around. So we have unnamed values, right? We have to connect those dots in our head that's how it works. So a benefit of this stack is it's quick and dirty and easy, and we didn't have to pre-realize all the variables or how big they are, all that stuff, right? Downside is that they're anonymous, they don't have names, so we have to remember what meaning they have when we're taking them from procedures. So now, having said that, if we consider that the stack might not be the best choice for parameters, what's the stack for? What's a good use for the stack? It must be good for something. Go ahead. When you need more variables than registers can offer, why don't you just create variables? Well, so is the stack. Yeah, I mean the stack is system memory as well, so it's not any faster or slower other than it's just there. So rather than
You're saying you're out of registers and you need to still store a bunch more data, or yeah.
or you can create a variable. Variables and registers are not the same thing.
Yeah, I know, but what he's saying.
But it's like, so like our registers and the stack both they're not like a variable isn't a register, is it? Or
Correct.
Yeah.
But a stack is not a register. Variables and stacks are based on system memory. Yeah.
So you
Might be built onto the CPU. Some CPUs have, depending on the architecture, have a stack memory built into it, but it's not register speed. It's a slower classification of memory. So why not just create more variables that have names?
Because stacks have a specific use that they're better for
For what?
when you need to use a stack data structure. I don't know.
No, okay, right. So that's what we're getting.
A playing card game. Pops the cards off the top. Of
Okay,
the
so
stack.
very specifically, they've incled the stack in the
Only
8086 for
yes,
card games.
Yes.
Exclusively. It's exclusively for card
Only
games.
used.
That's okay, makes sense. Can you think of it like a legitimate? It's pretty related to the idea of running out of registers, right? Isn't that a common theme for assembly programmers? Is we might run out of registers? Very common. It's a very common theme. All right, so, but sometimes we need to use a register temporarily, but we don't want to lose the value that's currently in the register. When we think about this in terms of operating systems, we call that context switching, right? Where we store the current value of the CPU's registers inside of some sort of data structure so that the next time a process circles back around and gets the CPU, it can unpack and get all the stuff back on the CPU. But now when we're writing logic and we have, we're leaving this procedure and going to this procedure, and we want to kind of free up our registers to be able to do stuff with them inside of this other procedure without worrying about overwriting stuff. a good thing that we could do is we can utilize built-in system calls or built-in Intel architecture calls. System calls would be on the DOS API side. We can use these built-in calls to go ahead and store all of the current values of our registers and flags on the stack, and then with a single call, restore them. So if we're going to do something and we're not relying on the current value of anything in our registers, we can then quickly push everything to the stack through, push A is a call that gets all of the registers onto the stack, basically giving you permission to now use any of the registers, even if you had previously used them, because now you're dealing with fresh values. Okay, and then when you're done, you do a pop A, and that restores all your registers to the previous state after you're done using them. That could be pretty convenient, right? Especially when we consider that we have a limited number of registers. Now, if we're going to rely on the stack for that, though, what does that then imply that we should not do? Definitely shouldn't mess with the stack without being very careful, right? Because we're kind of reliant on that whole push A, pop A thing doing its job, and if we start screwing with the the stack itself, we might break its functionality. Similarly, we then also have to be careful about our registers in terms of what we pass in, when we pass stuff in. If we're going to pass our parameters through registers, throw up. Oh, bloody nose. I was hoping it was throw up. It's so much better. Right? Yeah. See, we get it.
He's far enough away. All of us are in the splash zone.
Start getting under plastic like a Gallagher guy. Is that guy still around?
Who?
Gallagher?
No.
Okay.
He's not around.
You don't know who he is? He's a comedian. He used to just go up on stage and like smash vegetables. Just had a giant like sledgehammer, would just destroy.
Oh, yeah. Classic dude.
Yeah.
Watermelon giant mallet.
Yeah, him.
He's not a comedian.
No, I think he was. I mean, that was his brand of comedy. Yeah, I mean, people didn't find things that funny in the '80s, so yeah, that's what you had. You had that and Magnum PI. I mean, just those. that was it. Pretty limited. All right, so you would have to be careful about your use of registers because you might try to pass your parameters into a register, then do a push A, which would then put everything onto the stack, kind of taking things out of the register you thought you meant to push. So this is really moving us towards this idea of parameters stored in variables. Make sense? Now, we already kind of said that that variables aren't as fast as registers. So you are giving up a little bit of speed, but not that much speed, right? So now we start having that question: is things that need to be really, 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 really fast, we reserve our registers for those. Things that just need to be really, really, really fast, we're okay with variables. Okay, makes some sense? All right, so it didn't really matter how you did the homework assignment in terms of passing your parameters, but we wanted to get a feel for having that reusable procedure that can display stuff to the screen using the DOS API that took parameters in some sort of consistent means. All right, now, let's see, have we talked about, let's go here. So we're going to call this guy 8086 strings. All right, so, and we can think about this from the perspective of variables, but we're actually going to do a little Java today, implementing our own version of 8086 strings. All right, so what can you tell me so far about what you know about 8086 strings? They're bad. Compared to Java strings. So the 1968 string is just, it's just not there. It's not where it needs to be.
They're self-terminating.
Tell me what that means.
They have something
Okay, and what is that something?
Dollar sign.
Okay, dollar sign. So these guys are self-terminating. They're dollar sign terminating strings, all right, which is different than some other architectures, but that's an important aspect of strings, okay? What else can you tell me about strings? Whether it's something you've read about already or something you maybe have inferred from working with some of this stuff.
You don't know their own length.
Okay.
It's not going to be satisfactory for you.
Well, I want you to defend it. So that statement is kind of contradictory to what he's saying. What do you mean they don't know their own length?
There is no way. There's no bit of information in there that says I am a string that is length 7.
Well, you could write a function to do that.
So is that part of the string, or is that a function that you wrote for your string?
Well, in Java, you don't know that
Yeah,
each.
you do.
Well,
Well,
there's a function for
so the
each.
first thing we should do is we should make sure we put our the hat on that puts us in the right decade. Okay, we're talking about an architecture that's way, way before object-oriented programming, right? So the idea of having things that come with, come with methods and things like that. So when we talk about strings in Java, we think of them as these super, super powerful things that can hold a value, and then they have a whole bunch of methods that do stuff to them. That didn't exist back then in normal programming languages, let alone at this level. All right, so that's a true statement that strings didn't come with, a little side pocket that kept track of its length. But was their length calculable, computable,
Well, of course.
calculable hyphen computable? How? How might one calculate the length of a string? What pieces of information did you need to calculate the length of a string?
Just a string that you need, right? It's like
Offset of the variable.
Offset of memory?
Yeah, like so offset from the start point to your terminating symbol.
Okay. So if we're putting that in Java terms, we might say a pointer to the place in memory where the string starts.
Yeah.
Okay. So an offset off of the DS register, so our data segment where that variable starts, right?
Yeah.
Because when we start thinking about memory, I think we drew this picture last time, didn't we? Have we drawn the memory picture yet? Or was that in our evening class, Curcio? The memory picture? I'll just draw it again. I like drawing. All right. All right, so I'm going to make about 200 of these squares by hand. So it's going to take a bit.
It'll be worth it though.
I'm not going to make 200. Whoop, whoop, whoop. Oh, I think I just threw something away. Might have been important, who knows. All right, so we're going to think about our memory like this. Obviously, our memory is probably larger than this, but we can think of this as 1 byte steps. Because in 8086, it seems like everything's kind of a 1 byte in size. We have some 16-bit things, so some word size things are double bytes, but actually, double byte doesn't exist. It would be a word. Double word is 4 bytes. That's 32 bits. All right, so what does this guy visually look like to you, based on other programming stuff you've had before? Looks like an array. Okay, so a whole bunch of little cubby holes right next to each other, contiguous, right? So maybe this guy, so if we think about this, this is gonna be awesome. See how much less time this took this time? Look at that, boom. And then obviously, that would look like that. Okay, and let's just say this is, will 100 fit in there? No, we're going to go with single digits. Oh, whatever. No, we'll do 100. Okay, so we're going to say this guy has a base address of 100. Okay? Now, let's assume we're working in our data section, or our data segment, sorry. So we have our dot data in our code, and let me lift justify this so I can do some stuff. Okay. And let's say we create a couple of variables. So let's just create a variable. I want a variable called, let's say, param1, just to kind of stick with that thing. And this guy will be a dB. So that's going to be a data byte. We can give it an initial value if we want. So let's actually do, we'll make that guy equal to the string ABC. Okay? So something along the lines of the variables that you guys created for your homework assignment. All right, then we might have a param2. And this guy would be a dB XY Z L M N O P. Haha. Now I know my ABC. I practice that at least once a week.
It's the only way I can find out better than alphabet.
Really, you have to just start from the beginning and just keep going? All right, so we have a couple of variables. Now, we're going to say that, so somewhere down here, we have our DS register. And what's the DS register hold?
Data. Right?
Well,
The data section. That's what that is.
what about, see, well, you just keep talking yourself out of it.
I don't know, dude.
Confidence, go confidence.
No, I'm not.
So
So
DS, it holds the value of something. It is related to the data
section.
segment. Yeah, it's really, so what about,
Segment first. You looked at me like.
I don't think he did say segment first,
I
did he?
did say segment first. I said data. You can move on.
Well, no, you got to finish this. So what does it hold? So fine, it's
Oh, that's
related
not-
to the data segment.
Yeah, it holds all that stuff.
Oh, just it's all in there?
Yeah, sure.
How big is this register?
2.
It holds
3.
the pointer to where it's at.
That guy, right?
This dude's got it.
This isn't just infinite storage. It's that, like DS is a very special purpose. I mean, really, it basically, that register cost so much money. They took all available real estate on the CPU and just associated that with DS. Okay, so that guy's he's a 16-bit register, right? Just like AX or BX, any of those guys, he's not that big. All right, so he holds the offset. The base address is probably the for us right now the best way of thinking about this stuff. We use the offset keyword to get base addresses.
So would it be the offset of the data point, like dot data?
Offset of dot data from the beginning of the program, where this guy was loaded into memory. But for us, I think it's fair enough for us to say this is the base address of the data segment. So what gets stored in DS here, by our example right now, would be 100. That is the very first memory address associated with DS, the base address of DS. That make sense? We talked about arrays yet?
That might have been
No.
threw away.
Huh?
So that might have been what you.
What I threw away? Well, everybody in here has had the discussion about arrays with me because you've had at least 200 and probably 250, right? So we'll connect those dots for us from a historical sense. So if we're making an array, we'll go with a 4-bucket array here, and I'll finish our picture. And this would be green, of course. So in Java, we might do something like int array AR is equal to a new, actually, just to keep these examples equivalent, I'm going to create a byte array. A new byte array of size 4. Okay, even though that's not a common line that most of us have written in Java before, we're creating an array of 4 byte primitive types, which happen to take up 8 bits or 1 byte, which is going to allow us to make the direct correlation to this. Okay? So when we're looking at this in Java, AR is going to hold what kind of value? What kind of value will AR hold? A pointer? Memory address, right? Okay, it's going to hold the memory address. How do you know? As a Java programmer, when you look at this line, how do you know that's a memory address? The new keyword. New keywords are real estate agent. Goes and grabs someplace in memory. So when Java assigns the new keyword to go and run to the operating system and say, look, I need enough memory to hold this many of these dudes. So that means how much memory do I need then? What do you think, Connor? How much memory do I need to hold this many of these dudes? I made this one as easy as possible. How much? 4 what? 4 bytes. Because we have a byte, we have that many of them. 4 times 1 is 4. So we need 4 bytes of total real estate for this. Little small house, right? All right, so we went and asked the real estate agent to go and get us a big enough plot of land to give us enough space to hold 4 bytes. Okay? So the real estate agent, this guy right here, is going to run out, come back with the memory address, and just so we can connect it back to this slide, it just so happens to bring back the memory address 100, which means that this guy right here is 100. That guy right there is also bucket 0. This guy is 101, bucket 1, 102, bucket 2, 103, bucket 3. All right, and AR is said to point at this array. What it really does is AR holds the value of the base address of this array in memory. Make sense? So now when I say something like AR at bucket 2, here we'll go 9, 7, 5, 3. Those are our values that are in there, just so we have some values to play with. When I say AR at bucket 2, as a human being, we can immediately glance and say, oh, you want index 2, that's a 5. Nailed it, right? Okay. But what's actually happening under the hood? What does AR at bucket 2 actually mean? Go ahead.
The base address plus the offset.
This is AR plus 2 times size of, in this case, a byte. So that is base address is 100 plus 2 times size of byte is 1. So that is 102, which happens to be the memory address of bucket 2. That make sense? This is why arrays are stored in contiguous memory. This is also why when we get into, when you took CSC325, when we talk about data structures, this is why we say arrays are fast, linked lists are memory efficient. Arrays require contiguous memory, which means we have to have a big enough chunk of land to build the whole house on. Whereas a linked list, we could build one room here and one room over there and another room over there. They could be all over the place. So getting between rooms is inconvenient, but we can really maximize our efficiency in terms of the space we use. We don't need a whole lot of room for a single room, pun intended. Yeah. So, all right. So base address is what actually gets stored in our variable here. Walking through our array starts at the base address and then goes an offset from that base address. Make sense? This is how arrays work. Questions on arrays? All of us have seen this slide recreated before. Pretty much know what this guy is. All right. This guy, our memory, system memory associated with our 8086 architecture, we should think of as a gigantic array. Really, let's think about this. This is DS. Okay, this is the array that is DS. All right, so we have an array, if you will, called DS, whose base address is stored inside of DS that tells us where does this guy begin. And inside of DS, we have A, B, C. We're actually storing the ASCII values of those, but are we cool with this? Me putting actual characters in there? So I don't have to go look up ASCII values and then get confused myself, blah, blah, blah. Okay, so convert these to the ASCII equivalent. That's what's actually getting stored. All right, and this is 101, this is 102, so on and so forth. All right, so param1 is a data byte that's equal to ABC. Right? In actuality, it's ABC with a $sign at the end of it. So we have one extra little dude here, that guy, at 104, or 103, I'm sorry. Okay, so that is param1. Param2, oh, I put too many characters in this guy. X, Y, Z, looks something like that. And this is 104, 105, 106, 7, 8, 9, 10, and I might as well just finish it since we're this close. Okay, gotcha. So, in my little example here, we've pretty much exhausted our data segment for what the footprint I gave us. You would have more room than this. In fact, the data segment in modern assembly is because it's related to system memory, it is arbitrarily created. There's usually a maximum size that the operating system will allow to be grabbed by a system memory, but you don't have to worry about saying, well, I have to do all this in less than 6 variables or something like that. You have room. Same thing's true with 8086. There is a maximum, I don't know what it is, maximum data footprint of the data segment. It's going to be dictated by the model, the tiny model, small model, medium, those guys. So those guys dictate the combined maximum size of the data segment plus the code segment. So in the tiny model, I believe it's 64K kilobytes total between the two of them. In small, I think it's 64, and then it goes up from there for the size. So 64 kilobytes is 64 times 1,024 bytes. So we have 65,536 buckets in our array. Make sense? So more than what I've put here. We're good with that? All right, so I'm not going to do 65,536. Okay, so this is what our data segment looks like. This is actually how it's represented under the hood, as an array with all of our variables back to back. So these guys here are stored as pointers to their beginning spot in memory. So this guy right here actually is the pointer 100. This guy here actually is the pointer 104. Does that make sense? How do we get 100 and 104? If I wanted to move into AX, the value 100, well, the memory address associated with param1, how would I do it? So I'm down here in the code segment. And I want to move into AX. the value that is 100 as it relates to param 1. How do I get that?
Ram one, move it to Ram one.
Like that? What did I just put into AX? What's the value of AX after this? So far, we have no right answers. This answer is closer than that answer. Doesn't hold 100. This guy does not hold 100 right now. It also does not hold ABC.
ABC dollar sign?
Does not hold ABC dollar sign.
103.
103? Nope. I'm actually kind of impressed at the quantity of wrong answers that we're able to come up with here.
The offset of the start of the program, right, to your data segment.
Oh, this is the exact line you told me to write. I want to know what's in AX after that line. Then you can go back and give me the right answer. Because I think you figured out what the right answer should be by now. What is it? Another wrong answer?
Look at him, not me. I stopped answering.
Low confidence.
BA.
Who?
It'd be A.
B. Oh, it would be A. Say BA. Just reversing crap now, just starting from the middle. Yeah, it would be A. Well, the ASCII value of A, right? Whatever that is. What is that?
I don't know what it is in hex.
You would think, as long as I've been teaching this, I would have that memorized. I think at some point I did, and then I lost it.
Uppercase, lowercase is 61. in hex.
61, yeah.
97 in decimal.
Oh, you're looking at the simulator or the emulator, whatever. Yeah, at some point that was in there, but then it's unimportant. It's terrible.
So it is literally, well, not literally, but the ASCII value of A.
Yeah.
So
61, you said? So AX will be equal to 61 after this line. Did you put the line in? Did you try to test this?
No.
Oh, you don't have to, but if you want to, you'll see a 61 inside of AX.
So say you wanted to display numbers in assembly and you have the decimal version sorted in an array for sorting.
Not for any particular reason, right? So,
No.
yeah, so you guys are lucky in the 548 grad class, they're having to write a sorting algorithm in assembler. So that's your assignment for Thursday.
So I have it entering everything in and doing all
So you
that.
want to know how do you
I'm getting
display
two
a numeric value? Well, maybe you look up what the ASCII value is of those characters. Maybe write a procedure that looks at a number and then goes and finds the ASCII value of those guys.
Yeah.
Maybe off of an offset,
Yeah.
little 10 bucket array. You with me now?
Yeah.
All right. So now I have lost all hope. If he's asking that question, tonight's class is going to be horrible
Well, I mean,
because Huseman's in there.
well,
Okay.
they were not printing it or accepting values in.
So they had nothing. It was crap,
It was just a sort algorithm.
like in Java. They didn't even try it in assembler.
No, they did it in assembly, but that's it.
That's just an embarrassment. I get it. All right. So, who gave me the right? Oh, you gave me the right answer here. So when we move param1 in here, param1 holds the base address of this guy, but I'm saying here, give me the value at this. So if we were writing this in Java, this would be that param1 at bucket 0. That's effectively what we're writing if we're kind of throwing a Java template on top of this. That makes sense? All right. Now, what do I do if I actually want to get the value 100 by my example here? How do I get the 100 out of param1? There's actually two ways you can do this in 8086 assembler with the emulator. I've shown you one in class.
Isn't it you do the move SI param 1?
Actually, that actually would work, just because that automatically does something else. But let's pretend like that doesn't work. I want the special keyword here, because that makes more sense. It's more appropriate to what we're talking about. He actually said the word about 4 minutes ago, and we've said the word probably 10 times today.
Offset?
Offset.
Move SI, offset param 1, so it's basically the same thing.
Well, that would be true. But if you just move into SI, I think if you use the .org, it will automatically give you offset. So this guy will give you the offset of param1 as an address. Does that make sense? So if we were doing this in Java, well, actually Java doesn't have a syntax for pointers. If we were doing this in C++, offset of param1 is equivalent to address of param1. It's the address of param1. All right, there's actually another syntax in the emulator. I think it depends on which of the models you use, whether or not this works. But there's another syntax that will also give you the base address. Anybody know what it is? Maybe you saw it when you were looking at code from like a Google search or something. Okay, so at this address, so at param1 gives you the offset. I like the offset substantially more, but should both work, or at least they both have meaning, right? There are some things that look like they should work, but when you actually try it in the emulator, it gives you funky results because you put the wrong dot stuff up top or whatever. But we care more about how the underlying organization works in theory. Is Van asleep? Were you asleep? Are you lying? He looks so peaceful. He had his picture taken with Ada today. And I had my picture taken too, but I held the little Ada doll as well.
You didn't,
What was I supposed to do?
Mr. Gonzalez?
I would have brought Mr. Gonzalez if I remembered that it was Ada picture day. We could have had just a picture of Mr. Gonzalez and Ada just sitting on the chair. All right. So when I move into AX here, the offset of param1, I'm saying give me the base address of param1. So this will give me the 100. Make sense? Okay. So that's how I get that memory address 100. Similarly, if I move into AX, well, here, let's just do it as a separate line. Move BX, the offset of param2. Param2 is this guy, which actually is that memory address 104, which is the address immediately following the dollar sign that terminated our string here. So this is where that variable begins. So these variables are just lined up back to back to back. When our data segment gets processed, it's going to go through and it's going to say, oh, well, here's our first variable, throw that in memory. Okay, keep track of where we left off. Here's our second variable, throw that in memory. Keep track of where we left off, so on and so forth. Okay, we're just throwing all this stuff in memory so we have access to it during runtime in the code segment. Make sense? But in order to use param2, we need to tell ourselves where in memory param2's value actually lives. That's why we use the offset of param2 to give us this value, the first element of param2. Go ahead.
Is it possible to go from like the offset of like param1 and accidentally like jump like go into the memory range of param2, or is there some sort of safeguard in the assembly like it would be in a
No safeguard. No. So effectively, if we say add AX 7, I meant to hit 6, but I hit 7. That's fine. Good enough. And then I look at what's at that memory address. Well, it's going to put me right here. Yeah, so I just walked through memory. It lets you go right through it. And actually, what we're seeing here, that risk, that flexibility, that flexibility was exposed to us in an old language like C and C++. So remember when I introduced Java to you and I said that Java was kind of C++++, and one of the things they did, I mentioned that a lot of textbooks say that pointers don't exist in Java, when the reality is there just isn't a special syntax in Java for working with pointers. Java has removed our ability to directly manipulate memory. So Java took away that. So your question would have two separate answers. In assembler, in C, in C++, I'd have the same answer for you. No protection. We can just walk wherever we want. In Java, we're protected. We don't get to walk memory like that. We don't have a syntax for doing it. C# added back in a syntax for doing that inside of a special kind of code block. Anybody know what that code block is? It's unsafe. Unsafe code block. But yeah. I wonder. It's possible. C# has several macro things. So like, for instance, string in all lowercase and string in all uppercase works, so it's possible that unprotected is a thing. But it's definitely an unsafe code block will work. But that basically says, I realize I'm manipulating memory, just trust me. So C# has added that ability back in if you're willing to assume the risk. Because there are some situations where it is helpful to do pointer math. In fact, hopefully we're seeing here that in assembler, everything is pointer math. Everything is based off of a base address and it offsets off that base address. By the time we're done, we're all going to be counting in hex. Right? Isn't that fun? Don't you find this fun?
One that didn't even know the ASCII value of A.
Well, yeah. Why would I remember ASCII values when I just think of, I know the hex value, obviously.
What is it?
61.
That's the ASCII value.
Huh?
That's the ASCII value.
Yeah, but in hex.
Yeah. Oh, but in hex.
Got it. Nailed it. Pay attention in class.
Nailed it. I'll argue with that.
What was I talking about? Oh, pointer math. Yeah, so everything's pointer math. Okay, so this is our data segment. So when we want to start working with these strings, so we had our procedure, right, where we moved, what was it, AH9 was the print, is that print string? AH9?
Yeah.
Okay, yeah. AH9 was print string. Then we moved into, what was it, DX, the base address? I'm mostly making this stuff up. It was DX, right? So move AH9, move DX, the base address. The funny thing is my way my memory works, I'm actually reading this over here. It's messed up. It used to be way worse. That's why sometimes you see me point over here. I'm on medication, just trust me, it's fine. So move AH9, move DX, the offset of our variable, right? And then do an int 21H to interrupt the CPU, let DOS take over, do its magic, blah, blah, blah. And what's that guy going to do? It's going to start at that base address. So if we did that for this, so if we, here, let's come in here. If we do, actually, we're probably going to, here, we'll do that. Move AH9, then do int 21H. So we'll move into DX, the offset of param1. We'll move into AH9, system call 9. Then int 21H, this should display ABC to the screen. Right? Did it matter that I did these two lines out of order? I'm sorry, this won't display it to the screen. That'll be a weird error. Now it'll display it to the screen. Does it matter that I did the move DX and the move AH in different orders? No, they're mutually exclusive to each other, right? These two lines have nothing to do with each other than the fact that they are both required inputs, if you will, for an interrupt. AH is the required for the system call, and in this case, the single parameter is passed to DX. So the DOS API, this goes back to our discussion at the earlier in class, the DOS API is really set up almost a precedent for using registers for parameters. Has it not? Okay, so certain things we want to be fast. Why would it be important that writing something on the screen would be using a register instead of system memory?
You want that to be as fast as possible because otherwise the user's going to think there's a lag or...
Okay, and this maybe goes back to a generalistic statement that I/O is expensive. All right, and this is something, how many of you have had 350, and then how many of you are in 350 right now? Several of you are in 350 right now. Whether you've discussed it now or not, but one of the things you'll talk about is that I/O is really expensive. It's an expensive thing. You've seen it in some of my classes when I wrote a for loop that went through a million times, and if you just add, it happens instantly, but if you print to the screen, it takes forever to run. Okay, because I/O, input output, writing something to the screen is a really expensive thing to do. Right? There's a lot of work that goes into it, and now we see the reason why. In order to do I/O, what's the actual number crunching that's involved in 8086 DOS to do I/O? Move something into AH, move something into DX, then stop the CPU. Do you think that the average cycle through a CPU will allow a single program to do more than 2 single instructions? Probably. So we'll just pick a number. Let's say that the average cycle through a CPU, let's something do 100 instructions. I'm just pulling that out of here. It might not even be close, but let's say it's 100 instructions. Something way more than 2. All right, so I'm accomplishing 1/50th of what I potentially could be accomplishing on my turn through the CPU this time, because I'm doing I/O, because I'm writing something out to the screen. So I do my 2 little lines, I'm like, okay, I got nothing else to do here. The rest of this is up to the operating system. So the CPU gets interrupted. Now if we take that back over to the operating system side, what happens when a CPU gets interrupted? This is probably for those of you who've had 350. Because I'm assuming you have not talked about, yeah, you're going to do some context switching. And what's context switching?
Process off and let it process on.
Yep, so packing your bags. So context switching is in order for the next program to get loaded onto the CPU, the previous program has to pack up his bags, keeping track of where he left off, and leave the CPU. That takes time. It takes time to clean your room, okay, and put everything in nice little cubby holes. And then the next guy comes in and has to unpack his bags, put them in all the drawers and stuff like that, and put the stuff back into the registers to continue on. So you start seeing how these guys merge together, these two classes. So this goes back to Dr. Locklear's contention that computer science deals with the grand ideas of computer science, where all of these different topics are related. And we see the overlap all the time. We just like to think of certain classes being hard and other classes being less hard or something like that, right? When they're actually all trivial like this stuff. Oh, come on. Would you rather do this or write an English paper?
Yes.
Well, it depends. How long's the paper?
How many writing maybe you want to have?
It shouldn't matter. It shouldn't matter how long the paper is. This is your vocation. Should be fun. Right?
Don't think a lot.
Like you go and play video games at night instead of writing assembler?
Never.
No. Every night I go to bed. I mean, do you know how fast this puts me to sleep? The other day I was just thinking about my homework. Fell down 2 flights of stairs. Out cold. Yeah, she came up with this cockamamie thing of how she twisted her ankle. She was literally standing in the cafeteria thinking about the homework. Went down is what happened. All right, so that's why I/O is really expensive, is we're getting very little done on the CPU, relatively speaking, because we have to then say, okay, I've done as much as I can do. I've staged all these values inside of the appropriate registers. Now, DOS, you take it from here. All right, and if we're doing that for a million different numbers, we can imagine that starts adding up to time that a human being's going to start noticing. Right? For relatively few things, computers are fast enough that we're not really going to notice if we're inefficient. But for stuff like this, it starts adding up where nanoseconds over millions of times start turning into real seconds that we will start feeling, right? Okay, let's see. So we'll move into DX, the offset of param 1, which puts in there 100. Then we'll move into AH, the value 9, saying we want to print crap to the screen. We'll interrupt the CPU, telling DOS to take over. DOS then goes and looks in AH, says, oh, you want me to do magic trick number 9. Great. So what do you want me to print? Well, I'm going to go and look in DX. Like, oh, you want me to start at memory address 100 and do what? So if you're the DOS system command 9, print string to screen, how do you work? What's your algorithm? So I just, pulled you from the bullpen. We'll use some baseball talk, right? That they call it bullpen, don't they? Where the guy pitches, does the practice pitching? Isn't that the bullpen? Ah, nailed it. All right, and then so we're going to pull that guy from the bullpen. See, look, I know A and hex and baseball stuff.
Jack of all trades.
Yeah, seriously, just all over the place. So we're gonna call that guy in. He's gonna immediately look to DX for where he's supposed to start. Now, what do you think how does the algorithm work? If you were writing the algorithm for system call 9, how would you write that?
It just prints it.
You get to
I
see,
know, I was like, I don't
you get
know.
to see the concern in Dover's eyes, like,
It prints it.
I think I just heard her homework assignment. I didn't want to hear her homework assignment, but I think I just heard her homework assignment.
Well, I mean, it realistically just prints out to the screen of the variable that is inputted.
So that's what you're asking is how to write the system call that prints out to
Yeah.
the screen?
So
Let's say DOS. Let's say you didn't have the DOS API, so somebody hadn't already written that function.
So you look
So you wrote your own function
So
called.
is there a print command that I can call or no? Like,
Yeah, you have that function. You have the print single char function.
So it prints a single char. Well,
So
then
what
you-
you would do is you get that address of where that value is located.
and then do exactly.
Yeah, that's in DX.
Do this and then move forward size of char and then print again. Move forward
So you
size of
increment.
char.
Until
Dollar
what?
sign. Until
Ah!
$dollar bills, y'all.
Y'all. Okay. Until you hit the dollar bills, y'all. So you're going to go to the base address. So if you're this algorithm, you're going to say, oh, number 9. I know magic trick number 9. So you're going to zip over to memory here, wherever DX holds, which is memory address 100. You're going to say, is this guy a dollar sign? Nope, not the end of the string. Spit that guy to the screen or put it into a buffer, however it's implemented under the hood. But, get this guy on the screen. Then increment by 1. Increment by size of, you mentioned size of char. Why are chars bytes in assembler, in 8086 assembler? Huh?
Hex value.
Hex values,
So the ASCII equivalent would be stored as the hex value.
okay. Well, yes, that's how it's stored, but why is it a byte size instead of a 16-bit or a 32-bit value? Why is it 8 bits in 8086? Why are characters stored as 8 bits in 8086?
They don't need to take up more space, so why would they store them?
That's true. They don't need to take up more space, but why?
Because of what he said, that they're stored as hex values and not.
I can give you a hex value real quick that takes up more than 8 bits.
But not beyond the alphabet. Like you could go through all of the alphabet and then.
Well,
am I wrong?
what he's saying is he could give you it, but what would happen is it just cut it off and sort it into the
What is ASCII?
ASCII is a zero set or an 8-bit numbering system for letters and characters.
So ASCII is 8 bits, and it just so happens that our character sizes are 8 bits. Coincidence, right?
Oh,
Yeah.
did I say hex? I said hex. I meant to say ASCII. Back then.
Well, yeah, it's easy to say that now,
It is. It would
like a math thing. Like, I don't know why this reminded me of this, but years ago I was like an algebra class or something like that, and those word problems, right? And I think it was something with apples or something like that. I did all the math right, but I gave my answer in terms of oranges. I switched fruits, and the guy gave me a 0 on the question. Had the right numbers. Isn't that just kind of jerky?
Was it a little jerky of you to write?
No. I didn't do it on. I was just being. I don't even know how I switched fruits. No, I get it. If I was just being a smart ass. Yeah, no, that's not how it went down. It went down where I just flipped fruits.
Because you were thinking, oh, oranges sound better.
Well, or I'm crazy. One of the two. There's like, I'm reading crap over here, dudes. So, for all I know, I was doing my English homework and we were talking about orange plantations or something. Who knows? What was I talking about? Oh, Yeah, so the algorithm is going to start here. We're going to take sizes of 1 byte steps, so steps of size 1 byte, because the ASCII character set supports 256 unique characters. A lot of them are like playing cards and smiley faces and stuff like that, because the American Standard Code for Information Interchange, ASCII, decided, hey, the only thing that mattered was the English alphabet, right? Today, what's the replacement for ASCII? Unicode, which is 65,536 unique characters, the first 256 of which are identical. Make sense? All right, so we're going to have we'll have a quiz on Thursday where you're going to have to regurgitate the entire ASCII along with the hexadecimal and binary equivalents.
Good luck.
It's like, look, I'll just take the 30 with my name and just move on with life. All right. So the algorithm is going to go to the base address. It's going to keep putting a character out at a time until it finally gets to the $sign. And that's when it knows that this is the string termination character, and therefore I am done. Make sense? Okay. So, let's see if this guy runs now. What's neon 0.1? Was that there before?
I think it was just neon before.
Yeah. Well, that can't be more broken than it was before. Well, it's as broken. Nailed it. All right.
Can you click the drop down arrow and do it as something else?
I tried, yeah. Tried all these guys. Run as Java application.
There's nothing popping up in the background telling you
Mm-mm.
you're dummy or something?
No, I can accept the fact that I might be, but I've tried to do some investigation.
There's no like clean project? Can you do
Tried that too.
Well, I've run out of things then.
Yeah.
Sounds like you need to throw the computer away.
As soon as Apple comes out with a new MacBook Pro, I will. Okay. So in any case, what we want to do, and this is actually your homework. So we're going to create an 8086 Java string class. All right. So what we want in here is we want we're going to call this guy string 8086 because the word string is already taken in Java. So we're going to call this guy string 8086. So we're going to have a class named string 8086. This guy should be implemented as a char array. The constructor can take in a string but must convert /store as char, as $terminated char array. All right. So that's going to allow us to mimic a $terminated string. That make sense? Okay. Let's see. Maximum string size is, let's say 64. We'll just keep it simple. 64 chars. So all string 8086s should have a 64 character char array. And you'll take up some subset of those 64 buckets, terminating your character with a $sign. That make sense? So if you had the string hello you were trying to store, you're going to have 64 buckets, only the first 6 of which will have stuff in it. HELLO $sign. Make sense? All right. Then implement a print method that displays the contents of your string 8086 one character at a time until the end, not showing the $sign. You may not store the length of the string 8086. So we're mimicking 8086 strings from our assembly in Java. Makes sense what I'm asking you to do? So create a Java 8086 class. Its constructor will take in a normal Java string. It'll load that Java string into a 64-bit char array, or 64-byte char array, 64-bucket character array, terminating the end of that string with a $sign. And then you should have one method called print that will print that string to the screen one character at a time until its end. And its end is wherever it's terminated by a $sign. And
So
you're
we add the $sign. We take in a string.
correct.
We add the $.
Yep. Yeah, but you will store your $sign terminated string. Make sense? All right. I will see everybody on Thursday. I'll put this up on